This video we're going to discuss the guidelines for integration, basically the algorithm for general integration. We are going to discuss the following integration techniques. You can find the full slides of this lecture in the description of this video, and you can find the time codes for this video in the comments. So let's start with the substitution rule. So before we start, I would like to say hey, if you have the integration which fails to one of these cases, then you don't need to use any techniques, you can just use this table. So basically this is the table for integration of the standard functions, and here we're going to discuss how to integrate the non-standard functions which are not in this table. So first of all, so if you are given a function, try to simplify the function as much as possible. For example, in this case, we can just open up the brackets and we're going to have this term, square root of x plus x, which is possible to do the integration using the formula of the power functions, right? So if you are given this kind of function, sine of x plus cosine of x in the square, so first of all, we can try to simplify this by opening up the brackets. So this term is going to be written as a sine square of x plus t sine of x multiplied as a cosine of x plus cosine square of x. And we know that a sine square plus cosine square is going to be 1. And I can write down this term as 1 plus t sine of x cosine of x, and this is by the formula is simply the sine of tx, right? So integrating is again a straightforward, so the integration of 1 is x, and if this would be just the sine of x, it would be just minus cosine of x, but since this is sine of tx, it's going to be minus 1 over t cosine of tx because of this t. So let's start discussing the substitution rule. So the idea is like this. So if you see some function and its derivative inside the integral, then use the substitution rule. For example, if your function is given in this form, so the function multiplied to its derivative dx, then we can write down the u du, right? Or for example, your function g of x is inside the another function sine of x, and at the same time the derivative of this function is still here inside the integration, including the dx, and we can just use the substitution. G of x is going to be u, and as derivative multiplied as a dx is going to be du, right? So please note that if you decide to substitute the x with a u, you have to substitute all the terms in the integration with the new variable, including this dx. So let's consider a couple of examples. So here I see the derivative of the x squared minus 1 is here on the numerator. So we can make the substitution. U is equal to the x squared minus 1, then the u is equal to the tx dx, right? So here I don't have the t, so that is why x dx is going to be equal to the du over t, right? So if I write down du over t over u, it's going to be 1 over t ln of u. If I resubstitute the u with the x, it's going to be 1 over t multiplied as ln of x squared minus 1. So another example is when we need to integrate the sine of ln of x divided to the x, right? From here I see that there is some function whose derivative is also here inside the integration, right? So the derivative of the ln is 1 over x, which is still here, right? So this would be the idea of the substitution, right? So u is the ln of x, and du is 1 over x multiplied as a dx, or simply dx over x, right? So if I write down this integration in this form, sine of ln of x multiplied as a dx over x, we can substitute this with the u. It's going to be sine of u du, which is simply minus cosine of u, and if we resubstitute this back, it's going to be minus cosine of ln of x. So let's continue discussing our integration techniques on the trigonometric integration. We're going to talk about the integration of the trigonometric functions in this form, where we're going to multiply the sine and the cosine with different powers. Okay, so we're going to differentiate 3 types of the this kind of cases, trigonometric integration, when we multiply the sine and cosine. So the first case is when the power of the cosine is odd. Okay, so no matter what is the power of the sine, so if the power of the cosine is odd, we can use the following algorithm to integrate this. So the idea is like this. So if the power of the cosine is odd, then it can be written as the cosine in the power of tk plus 1, right? So we need to save one term, split one term from this separately, and express the other all the other terms using this sign in terms of the sign. So for example, I can write down the cosine of 2k plus 1 in terms of the cosine 2k multiplied as the cosine of k, and I can write down this cosine in the power of 2k in terms of the sine in this form. So basically I'm going to write the cosine 2k as the cosine square in the power of k, right? And at the same time, cosine square is 1 minus sine square of x, right? So now we can just use the substitution. U is going to be sine of x, and du is going to be the cosine of x, right? So I found some function whose derivative is also here, right? So then I can just substitute this thing with the u in the power of m. This thing is going to be u minus 1 minus u squared in the power of k, and this thing is going to be du. So let's consider an example. So we're given a trigonometric function where the power of the cosine is odd, right? So as we discussed before, we're going to split this into the two terms where one cosine is going to be separate, right? And we're going to express this cosine square in terms of the sine using this formula. And now we can introduce the substitution. U is equal to the sine of x, du is equal to the cosine of x dx. So after the substitution, we're going to get this term, so which is really easy to integrate. It's going to be u cubed over 3 minus u5 over 5. So at the end, you just need to resubstitute the u with the sine of x. So another case is if, for example, the cosine's degree is not odd, right? But at the same time, if the power of the sine is odd, then we're going to use the same technique. Okay, so no matter what is the degree of the cosine, if the power of the sine is odd, we're going to again split the sines into the two. We're going to basically save one sine factor and express everything in terms of the cosine. So the same technique, the cosine of in the power of m multiplied to the sine in the power of 2k multiplied to the sine dx, and we are going to express the sine in terms of the cosine by writing this 1 minus cosine squared in the power of k. Okay, so by introducing the substitution u is equal to the cosine of x, du is going to be minus sine of x dx. We can express everything here with the u and du, with the new variable, right? So it's going to be u in the power of m multiplied as the 1 minus u squared in the power of k multiplied as minus du, right? So if the du is minus sine of x dx, then sine of x dx is minus du. So let's consider an example. So we're given a function where the power of the sine is odd, right? We're going to save one power of the sine, so one sine separately, and we're going to express the rest of the sine using this function. So here, the cosine square of x, sine in the power of 4x is going to be written 1 minus cosine square of x in the power of t, right? So since 1 minus cosine square of x is sine square of x, everything is true. So we're going to introduce the substitution. U is going to be cosine of x, and du is going to be minus sine of x dx. So by introducing the substitution, we're going to have this term, right? So u squared, 1 minus u squared in a square. So if you open up the terms here, it's going to be 1 minus 2u squared plus u in the power of 4, right? If you multiply everything to the minus u squared, it's going to have this form. And by integrating everything here using the power functions, this is pretty much straightforward. It's going to be 2u5 over 5 minus u3 over 3 minus u7 over 7. So if both of the powers are even, then we need to try to decrease the powers degrees using the formulas of the half an angle. So basically, sine square of x can be written as a 1 minus cosine of tx over t, and the cosine square of x can be written as 1 plus cosine of tx over t. And at the same time, you can know that this formula, so sine of tx is actually equal to the 2 sine of x multiplied to the cosine of x, right? So for example, so if our function is given in this form, sine square of x, so theoretically we can write down this. So we can write down this as a multiplication of the two functions with the even powers, sine square of x and the cosine in the power of 0, right? So here we're going to decrease the power of the sine using the formula 1 minus cosine of tx over t, right? And the rest is pretty much straightforward. So the integration of the 1 is going to be x multiplied to the 1 over t, and integration of the cosine of tx is going to be sine of tx over t multiplied as a 1 over t, right? Or another example would be sine of x multiplied as a cosine of x, which can be simply written as sine of tx over t, and by integrating this we're going to get the answer minus cosine of tx over 4. So another type of the trigonometric integration where we're going to consider is we are given the multiplication of the tangent and the secant and different powers. So we are going to differentiate again the two cases. The first case is when the power of the secant is even. Okay, so no matter what is the power of the tangent, if the power of the secant is even and more than 0, we're going to say factor secant square, and we're going to express everything else in terms of the tangent. Okay, so if this power of the secant is even, we can write down this as a tk, right? Because no matter what is a k, it's going to be always even number. And we're going to split one, like a secant square separately. If you subtract, divide everything to the secant square, it's going to be 2k minus 2, right? Which you can written as the secant square in the power of k minus 1, right? And now we're going to express everything else in terms of the tangent, because we're going to introduce the substitution. U is equal to the tangent, du is equal to the secant square. So this term is going to be u in the power of m. This term is going to be 1 plus u squared in the power of k minus 1. And this term is going to be du, right? And integrating this is pretty much straightforward because we just need to use the integration of the power function. So let's consider this example. Here the power of the secant is even, right? We're going to write down this as a secant in the square multiplied as a secant in the square. So we're going to save this for the du, right? And now we need to just express the secant square in terms of the tangent square. So by the formula 1 plus tangent square, we can write down this the secant square, right? So here the substitution is u is equal to the tangent of x, du is equal to the secant square of x dx. By introducing all the substitution, this is going to be u in a square, this is going to be 1 plus u in a square, this is going to be du, right? So after the integration, we can simply get the answer. So the next find, let's say find the power of the secant is not even, okay, it's odd maybe. So, but if the power of the tangent is odd, we're going to use the following algorithm for integration. So the idea is, so we need to save one term of the tangent and one term of the secant separately, and try to express everything else in terms of the secant. Okay, so if the power of the tangent is odd, we can write this in the form 2k plus 1, right? Because no matter what kind of integer k we put here, so 2k plus 1 is going to be always an odd number. So we are going to split one tangent separately. So this is tangent 2k, right? And we're going to separate one secant separately. So secant in the power of n minus 1. So now we're going to use the substitution. So our substitution is now first of all we're going to express the tangent square in terms of the secant square. So the secant square minus 1 is going to be tangent square, right? Because you remember the tangent, the secant is 1 over cosine. Secant in the square is 1 over cosine square. So 1 over cosine square minus 1 is going to be 1 minus cosine squared over sine over cosine square. It is sine square over cosine square, which is tangent square, right? So now we're going to introduce the substitution. U is going to be secant, and derivative of the secant is secant of x multiplied as the tangent of x multiplied as a dx, right? So this term, so with the dx, is going to be du, and everything else can be written in terms of the u, right? So this is going to be u squared minus 1 in the power of k, this is going to be u in the power of n minus 1, and this is going to be du simply. So let's consider an example. So the power of the secant, it doesn't matter what is the power of the secant. So the power of the tangent is odd, and I'm going to express the tangent. So 1 power of the tangent is going to here, and 1 power of the secant is also going to here. So this is going to be our du, right? So now we need to express the tangent square in terms of the secant. So we can write this as a secant square minus 1. So by introducing the u is equal to the secant, we can write down here u squared minus 1 multiplied to the u cubed multiplied to the du. So the integration of this term is pretty much straightforward. So this is going to be u in the power of 6 over 6 minus u in the power of 4 over 4. So the next topic which we're going to discuss is the integration of the rational functions. We call the function as a rational function where it comes with the ratio of the two polynomials, right? So the idea of integration of the rational function is to express the rationals as the sum of the linear factors, like express the denominator of the rational functions as the multiplication of the linear factors. So basically, for example, if we're given a function, the rational function x plus 5 over x squared plus x minus t, we can write this as t over x minus 1 minus 1 over x plus 2. So, and if we have to integrate this rational function, we can simply integrate this t easily, right? And so in order to prove that they are equal, so we can just give the common denominator and show that once we give the common denominator, the denominator is going to be x squared plus x minus t, and numerator is going to be x plus 5, right? So if you give the common denominator, it's going to be t multiplied as x plus t minus x minus 1, it's going to be x plus 5. So now, so how did we know that this number is here t and this number is 1? So basically, what is a general algorithm? So the first of all, we're going to consider the three cases. The first case is where the denominator can be written as the product of distinct linear factors. Okay, for example, in this case, the x squared plus t minus t can be written as x minus 1 multiplied as x plus 2. So if it is possible to write the denominator as a product of distinct linear factors, then we're going to write down this rational function as one constant divided to the first linear factor plus another constant divided to the second linear factor, right? Similar to here, right? Some constant divided to the first linear factor plus some constant divided to the second linear factor. So the only problem is here to find what is the a and what is the b, or figure out how to find a and b. So the idea behind this is, again, so given the common denominator here, we're going to write down, we're going to get some rational function, and at the end we're going to equalize this rational function with this one, was the original one. So if we give the common denominator, it's going to be written a multiplied as x plus 2 plus b multiplied as x minus 1, right? If I open up the brackets and if I regroup this in terms of like x and the powers of the x, it's going to be written a plus b multiplied as x plus ta minus b. So you see, so the denominators are the same. And if I want that these two rational functions are the same, so the numerators should be the same as well. So the two polynomials are the same if and only if their coefficients are the same. Right? So basically, a plus b should be equal to the 1, the coefficient before in front of the x, and ta minus b should be 5, right? So by solving this system, a plus b is equal to the 1, and ta minus b is equal to the 5, we can find that the a is equal to the 2, and b is equal to the minus 1, right? Indeed, if you put the a to be equal to the 2 and b to be equal to the minus 1, you will get the 1 here for the first equation, and 5 here on the second equation. So let's consider an example. So we're given the term dx divided to the x squared minus 4. So the first step is to write down the x squared minus 4 in terms of the multiplication of the linear factors, right? So now we can write down this rational function in terms of some constant multiplied divided to the first factor plus the constant divided to the second factor, right? So we want this polynomial or this rational function to be equal to this one, right? So by giving the common denominator, we can write down this polynomial like this, and so now the second step is we need to regroup the numerator. We need to write this in terms of the polynomials, right? So in terms of the powers of the x. So if I take out the x from here and here, it's going to be a plus b as a coefficient of the x, right? And the rest is going to be ta, which is here, minus tb, which is here. So now I need to solve the system. So a plus b should be equal to the 0, right? Because the coefficient of the polynomial here in front of the x is equal to the 0. And ta minus tb is going to be 1 because the free coefficient here on the left hand side is equal to the 1. So by solving this system, I'm going to get the answer a is equal to the 1 over 4 and b is equal to the minus 1 over 4. So indeed, if you substitute a and b like this to here, it's going to be 0, right? So this is 0 here. And if you substitute 1 over 4 here and minus 1 over 4 here, if you sum them, you're going to get 1. Okay, so numerator here is going to be 1, which will be the same as this rational function. So now the integration of this function is going to be the integration of these two functions and their sum. So it's going to be 1 over 4 divided to the x minus 2 dx plus minus 1 over 4 over x plus 2 dx. So this is the ln of x minus 2, this is minus ln of x plus 2, so you can write this down as a 1 over 4 multiplied as the ln of x minus 2 over x plus 2. So the second case of the rational functions is when the denominator of the rational function can be written as the product of the linear functions, linear factors, but some of them are repeated. So in this case, the algorithm of finding the linear factors of the rational functions is slightly different. So we need to write, in this case, for example, so we're going to write down the a divided to the x minus 1 plus b divided to the x minus n square plus c divided to the x plus 1. So basically, you see, so if your linear factor is repeated, you're going to write repeated twice, you're going to write two terms here. If this would be repeated like 3 times, we would write here 3 terms until we reach the last power degree, right? For example, if this would be x minus 1 in the cube, the terms here would be a divided to the x minus 1 plus b divided to the x minus 1 in the square plus c divided to the x minus 1 in the cube. Okay, so by given the common denominator and by equalizing the coefficients of the two polynomials on the left and on the right hand side on the numerators, we can find the values for the a, for the b, and for the c. Okay, so by finding the values of the a, b, and c, we can simply integrate this. So the next case is where the denominator q contains irreducible quadratic factors. For example, so the denominator can be written as the x multiplied as x squared plus 4, right? Where this factor is not reducible more, right? So I cannot write this as a multiplication of the linear factors. In this case, I'm going to write down the polynomials in this form. So a divided to the x, which correspond to this first linear factor, and bx plus c over x squared plus 4. Okay, so I'm going to write here a polynomial 1 degree less on the denominator. So again, by giving the common denominator and by equalizing this polynomials, two polynomials on the numerators, the same method as we showed in the case 1, we can find the coefficients a, b, and c, and then we can integrate them using this all the techniques which we have learned so far. So one of the most important techniques in the integration is called the integration by parts. So this corresponds to the multiplication rule for the derivatives. So the basic idea is here, if you have the multiplication of the two functions inside the integration, so we need to get rid of one of them. So the integration by parts helps us to do this. So let's say you have the integral in the form. So one function multiplied to the another one, but you know that this is the derivative of another function g. Okay, so if this is the case, you can write down this function as the f of x multiplied to the g of x minus g of x multiplied to the f prime of x. So the basic idea here is that so we need to get rid of the one of the functions by integrating or differentiating. Okay, so by introducing the substitution, u is equal to the f of x and dv is equal to the g prime of x. So if you find du, it's going to be f prime of x du dx, right? And v is going to be g of x, right? So we can substitute everything, all the terms here with the u du and v dv, and we're going to get the formula which is more easier to remember. So it's going to be u, which is f of x, multiplied to the dv, g prime of x dx is equal to the uv minus v du. So let's do a couple of examples in order to understand this. So let's say we're given this function, the multiplication of the two functions. The basic idea again, so the main idea, we would like to get rid of one of the functions, right? So if I choose the u to be equal to the x, in the next integration, when we use the du, the x is going to be disappeared, right? So u is equal to the x, du is equal to the dx, dv is equal to the sine of x dx, and v is the integration or the antiderivative of the sine of x, which is minus cosine of x. Then u dv is equal to the uv minus v du. We're just going to substitute vu from here and v du from here. So uv is going to be x multiplied to the minus cosine of x, and v du is going to be minus cosine of x multiplied to the dx, right? So it's going to be with the plus, and integration of the cosine is simply sine of x. So again, the idea of the integration by parts is we're going to get rid of one of the functions if we have the multiplication inside the integration. So the last topic, the last integration technique which we're going to discuss at the end is the integration of the radicals. So basically, if we're given some function inside a square root, in order to integrate this, we need to get rid of the square root, right? So we need to introduce such a function, such as substitution, which will help us to get rid of this square root in order to eliminate, so which help us to eliminate the square root. So if your function is given in the form a squared minus x squared from the square root, then use the substitution. X is equal to the a multiplied as the sine of u. Because if you substitute this x here, it's going to be a squared minus a squared multiplied to the sine of square. So at the same time, do not forget to substitute the dx as well, right? So if the x is equal to the a sine of u, then dx is going to be a multiplied to the cosine of u du, right? So once we substitute the x, we have to substitute the dx as well. So from here, from the square root, I can take out the a squared, and what is left is 1 minus sine square of u. So by using this equality, this identity, we can write this as a cosine square of u. So after we simplify everything, it's going to be a squared multiplied to the cosine square of u, which can be integrated using one of the tools which we have learned so far. So if your integration is given in the term a squared plus x squared, then in order to get rid of the square root, we're going to use the following substitution. X is going to be a multiplied as a tangent of u, and we're going to use this identity. 1 plus tangent of square is going to be equal to the secant square, right? So if you substitute the x with this, so we have to substitute the x with the new variable as well, right? So this is going to be derivative of the tangent, which is secant square of u multiplied to the du. And this integration is going to be a squared plus a squared tangent square multiplied to the dx, which is a multiplied to the secant square of u, right? If you take out the a squared from the square root, it's going to be just the a, and what is left is 1 plus tangent square, which is going to be secant square, right? So 1 plus tangent square is going to be secant square, so this is going to be simply secant, right? So if you multiply a to the a, it's going to be a squared, secant square multiplied to the secant is secant cube. So there is some rules how to integrate, how to find the integration of this integrate. So the last case, the very last case, if your integration function is given in the form x squared minus a squared. So this is a little bit different form than before, right? Previously it was a squared minus x squared. So if this is the case, then use the following substitution. X is equal to the a multiplied to the sine of secant of u. Then use the identity. Tangent square is equal to the secant square minus 1. Okay, so again, so we are going to substitute the x squared with the a secant of u, and dx is going to be substituted with the a secant of u and tangent of u. So if you substitute the x with the new substitution here, you can take out the a's from the brackets, right? What is left is secant square minus 1, which is equal to the tangent square. From the square root, it's going to be just a tangent. And you can write as a square multiplied to the secant multiplied to the tangent square. And you can write down the tangent square as a secant square minus 1. If you multiply this as a secant, it's going to be secant cube minus secant. So both of the integrations are possible to integrate. So this was the guidelines how to integrate the non-standard functions. So obviously these methods are not include many more integrations. So if you would like to, if you couldn't integrate your integral using these methods, then one of the easiest ways would be to just find evaluated integration numerically using the computer programs, unless you're not in exam.